most important topic in this course. The inventors of BJT received Nobel Prize in Physics. Now you can guess how important this topic is. The transistor was invented in December 1947. The transistor was invented in December 1947 by the team of John Bardeen, Walter Brattain, and William Shockley at Bell Labs. USA. The head of the team was William Shockley, and later he invented junction version of the transistor. William Shockley invented junction version of transistor in 1951. They received Nobel Prize in 1956 for the invention of transistor. John Bardeen is the only physicist who received 2 times Nobel Prize in physics. The first one was in 1956 for the transistor. The second one was in 1972 for BCS theory. And this is the image of first transistor invented by the team of William Shockley. And the invention of transistor was revolutionary, and transistors replaced bulky vacuum tubes. This is the image of vacuum tube, and this is the image of modern day transistor. BJT is a 3-terminal doped semiconductor device, and it is used in amplification of weak signals and switching operations. BJT, the bipolar junction transistor, is a 3-terminal device, and it is used in amplification of weak signals. It is used in amplification of weak signals, and it is also used in switching operations. So there is use of BJT in both analog and digital electronics. The next thing is physical structure of BJT. We have 2 types of BJT. The first type is known as NPN transistor, and the second type is known as PNP transistor. In case of NPN transistor, P-type semiconductor material is sandwiched between 2 N-type semiconductor materials. In case of PNP transistor, N-type semiconductor material is sandwiched between 2 P-type semiconductor materials. There are 3 regions in transistor. The largest region is called as collector region. The smallest region is called as base region. And this region here is called as emitter region. The terminal connected to the emitter region is called as emitter terminal, or simply emitter, and it is represented by capital E. The terminal connected to the base region is called as base terminal, or simply base, and it is represented by capital B. And this terminal is called as collector terminal, or simply collector, represented by capital C. As we have 3 regions, 2 junctions are formed. Let's say this junction is junction J1 and this junction is junction J2. Junction J1 is formed between emitter region and base region. Because of this, we call junction J1 emitter base junction. Junction J2 is formed between collector region and base region. Because of this, junction J2 is called collector base junction. If you remember the presentations on PN junction diode, we had 2 regions, P, N, and because of this there was only 1 junction. Here we have 2 junctions, J1 and J2, because there are 3 regions. In case of PN junction diode, there was depletion layer across the junction. In the same way, we have depletion layer across junction J1 and depletion layer across junction J2. I will explain these things in great detail in the coming presentations. The same thing will happen with PNP transistor. This terminal is emitter terminal, this terminal is collector terminal, and this terminal is base terminal. Now I will compare the width of the 3 regions. Collector is having the maximum width, then we have emitter, and base is having the minimum width. Now I will compare the doping. Emitter is having the maximum level of doping. Then we have collector, and base is having the minimum doping. Size or width of collector is maximum because it has to collect the electrons and heat is produced in it. So if width is more, better heat dissipation will be there. The next thing is the cross-sectional view of the transistor. I will quickly draw the cross-sectional view of the transistor. This is the cross-sectional view. This region is emitter region and this terminal is emitter terminal. This region is base region and this terminal is base terminal, and the largest region is collector region and this terminal is collector terminal. This is the cross-section view of NPN transistor. You can also draw the cross-section view for PNP transistor. Everything will remain same. The only thing you have to do is to replace the two N-type materials with the P-type materials and this P-type material with the N-type material. The next thing is the symbol of transistor. We represent transistor by this circle in which this vertical line represents the base. This is the base terminal. This line represents the emitter and this line here represents the collector. This is emitter terminal, this is collector terminal, and we have to differentiate between NPN and PNP transistor. So I will copy this and paste it so that we have two similar symbols. This symbol is for NPN transistor and this symbol is for collector terminal, and we have to differentiate between NPN and PNP transistor. So I will copy this and paste it so that we have two similar symbols. This symbol is for NPN transistor and this symbol is for PNP transistor. Now to differentiate between the symbol of NPN transistor and symbol of PNP transistor, we have to mark the direction of current. This is base terminal, this is emitter terminal, this is collector terminal. In the same way, we have base terminal, emitter terminal and collector terminal. In case of NPN transistor, the electrons will move like this from N side to P side. So direction of current is from right to left, from P side to N side, or you can say from base to emitter. So we have direction of current like this from base to emitter in case of NPN transistor. On the other hand, in case of PNP transistor, the electron will move from N to P. So direction of current is from emitter to base. So the direction of current is opposite. In case of PNP transistor, it is from emitter to base. So this is how we differentiate between the symbols of NPN transistor and PNP transistor. I hope it is clear to you. We will use these symbols a lot in this course, so it's a good time to understand the meaning of this arrow in the transistor symbol. The next thing is the meaning of name, the meaning of bipolar junction transistor. But before that, there is one more thing that I want to explain. You can see we have two junctions and three regions. So it is like two PN junctions connected back to back. The transistor may be regarded as a combination of two diodes connected back to back. That's why knowledge of diode is very important to understand the transistors. Generally, NPN transistor is used because mobility of electron is more than mobility of holes. Now we will move to the meaning of name. Why we call transistor as bipolar junction transistor. We have already seen the meaning of junction. We have two junctions in transistor, and now we have to understand meaning of bipolar. There are two types of charge carriers in transistors, and they are electrons and holes. Electrons are negatively charged and holes are positively charged. So we have two types of polarities. Because of this, we call transistors bipolar device. The name transistor is made of two words. The first word is transfer. And the second word is resistor. We have two junctions in transistor, J1 and J2. If junction J1 is forward biased, it will offer very low resistance. If junction J2 is reverse biased, it will offer high resistance. Weak signal is introduced to the low resistance and output is taken from the high resistance. Thus BJT transfers a signal from low to high resistance. So there is prefix trans, because BJT is transferring the signal from low to high resistance, and this prefix trans is taken from the word transfer. Transistor falls in the family of resistor, so we have Istor, I-S-T-O-R, Istor in the name of the transistor, and we have taken it from the word resistor. So this is how we have this name transistor. I hope it is clear to you. The last topic in this lecture is regions of operation. As we have two junctions, we have four possible ways of biasing the transistor. In case of diodes, only two types of biasing was there, forward biasing and reverse biasing, because of one junction. But in case of transistor, we have two junctions, and thus we have four possible ways to bias the transistor. I will quickly make the table. In the first column, we have the emitter junction, or you can say emitter base junction. In the second column, we have collector base junction, and in the third column, we have regions of operation. The first column is for junction J1, the emitter junction. The second column is for junction J2, the collector junction, and the third column is for region of operation. When junction J1 is forward biased and junction J2 is reverse biased, the region of operation is active. When operating point is in active region, or you can say the transistor is in active mode, the transistor operates as an amplifier. In this reason, the transistor operates as an amplifier. When junction J1 is forward biased and junction J2 is also forward biased, the transistor remains in saturation mode, and it corresponds to the logical on or closed switch. In the third case, junction J1 is reverse biased and junction J2 is also reverse biased. In this case, the transistor remains in cutoff region. And it corresponds to logical off or open circuit. And in the last case, junction J1 is reverse biased and junction J2 is forward biased, and in this case the transistor is inverted. And it is like we are switching emitter and collector. This mode of operation is rarely used. And in this mode, emitter and collector switch their roles. This is all for this lecture. If you have any doubt, you may ask in the comment section. In the next lecture, I will explain working of transistor. And the three terminals are base, emitter, and collector. Because of this, we have three transistor configurations. The first configuration is common base configuration. The second configuration is common emitter configuration. The third and last configuration is common collector configuration. Out of these three, common emitter configuration is mostly used because of various advantages. In this lecture, I will explain common base configuration. In common base configuration, base is common to input and output circuit. This is input circuit. This side is input side and this side is output side. If you see the direction of emitter current in the transistor symbol, you will find this transistor is an PN transistor, in which this is emitter, this is collector, and this is base. So base is common to the input circuit and the output circuit, and it is grounded in common base configuration. I am calling this side input side and this side output side because weak signal is introduced on this side, and we have amplified signal on this side. and this will happen only when the transistor operates in active mode. So there is amplification of weak signal in active mode. There are two junctions in transistor, junction J1 and junction J2. In active mode of operation, junction J1 is forward biased and junction J2 is reverse biased. Junction J1 is the junction of diode EB. Junction J1 is the junction of diode EB. Junction J2 is the junction of diode BC. Junction of diode BC. We can consider transistor as two diodes connected back to back. So diode EB is forward biased and diode BC is reverse biased in active mode. I will forward bias EB. Let's say this resistance is RE. Emitter is N-type material and base is P-type material. So emitter is connected to the negative terminal and base is connected to the positive terminal, and I will call this forward biasing potential VEE. Now I will reverse bias the diode BC. This resistance is RC. Collector is N-type material and base is P-type material. So to reverse bias BC, collector is connected to the positive terminal and base is connected to the negative terminal. I will call this reverse biasing potential VCC. If I compare diode and transistor, diode is a single port device, and transistor is a two port device. In case of diode, we have simple VI characteristics. But in case of two port devices like transistor, we have input and output characteristics. In case of input characteristics, we have plot between the input current. The input current in this circuit is IE, the emitter current, and the input voltage is VBE. And in case of output characteristics, we have plot between output current is IC, and output voltage is VCB. So the next thing is to find out direction of currents IE, IB and IC, and what is this voltage VBE and this voltage VCB. From the symbol of transistor, you can see the direction of emitter current IE is like this, and direction of base current IB is like this, and direction of collector current IC is like this. If you don't know how we have obtained these directions, then please watch the previous lecture. I have explained how we have these directions in the transistor circuit. VBE is this potential. If you neglect RE like I did in the previous presentation for the sake of simplicity, then you will have VBE equal to VEE. This is what we have. In the same way, VCB is the potential difference across the base and collector, and VCB is equal to VCC if we neglect RC. Now there is one very important thing that I want to explain. You cannot write VBE as VEB. If you follow the proper nomenclature, you cannot write VBE as VEB, because B is at higher potential and E is at lower potential. So B will come first, then will come E. In the same way, if you see the collector, it is at higher potential and base is at lower potential. So in representation, C will come first and later will come B. So this is important thing. If you follow the proper nomenclature, you have this representations for input voltage and output voltage. I'm not going to explain the input and output characteristics in this lecture. We will continue with them in the next lecture. In this lecture, I will use KCL to obtain the relation between the emitter current, the base current and the collector current. We already know from Kirchhoff's current law, the sum of entering current is equal to the sum of leaving current. In this circuit, you can clearly see IE is the leaving current and it is the only leaving current, so it is equal to IB plus IC, because they are entering currents, IB plus IC. So this is the first equation that we have in this lecture, and it is very important. There is one more thing that you must keep in your mind. This equation is true for active mode of operation only. The next thing is the collector current. The collector current IC is equal to alpha times IE plus ICO. This is the reverse saturation current. I will rename the reverse saturation current. For the common base configuration, I will add B in the representation, or IC is equal to alpha times IE plus ICBO, where this B stands for the common base configuration. The next thing is the comparison between the emitter current IE and the reverse saturation current ICBO. This O stands for open circuit because we measure this current when the emitter terminal is open. When we compare IE and ICBO, the emitter current is greater than the reverse saturation current, because reverse saturation current is due to the minority charge carriers and they are very small in number. So we can neglect ICBO, and IC, the collector current, is simply equal to alpha times IE. So we can say that alpha is equal to IC divided by IE. This is very important relation. Alpha is equal to IC by IE. Now what is alpha? Alpha is common base current gain. Alpha is common base current gain, and you already know gain is equal to the output by input. IC is output current and IE is input current. So alpha is the common base current gain, and it is also called as amplification factor. Amplification factor. So these are the two names for alpha, and alpha is between 0.95 to 0.98. This implies 95% to 98% emitter current is the collector current. And this also implies there is 5% recombination in base, and in this case there is 2% recombination in base, and base current IB is equal to 1 minus alpha times IE. So these are the important relations that you must note down, and I think this is all for this lecture. If you have any doubt, you may ask in the comment section. In the next lecture, I will explain how to obtain the input characteristics in case of common base transistor.